A spark jumps through the air. A compass turns beside a wire. A radio antenna sends an invisible signal, and sunlight crosses millions of kilometers of empty space. These phenomena look completely different, yet they are expressions of one connected system, electromagnetism. James Clerk Maxwell captured that system in four equations. They explain how charge creates electric fields, why magnetic field lines never end, how changing magnetism creates electricity, and how changing electricity creates magnetism. Most remarkably, the equations predict a self-propagating wave. When its speed is calculated, the answer is the speed of light. In this lesson, we will build that connection visually, one idea at a time. Before reading Maxwell's equations, we need the language they use. A field assigns a value to every point in space. An electric field tells a positive test charge which way it would accelerate. A magnetic field tells a moving charge how its path would bend. Each arrow therefore carries both magnitude and direction. Two local patterns matter. Divergence asks whether arrows spread outward from a point or converge inward. It detects sources and sinks. Curl asks whether the arrows tend to circulate around a point. Maxwell's equations combine these two patterns with charge, current, and time. So instead of treating the symbols as decoration, imagine tiny probes measuring what the field is doing everywhere. Place a positive charge inside an imaginary closed surface. Electric field arrows leave the charge and cross the boundary. Adding the outward contribution over the complete surface gives electric flux. Gauss's law states that this net flux equals the enclosed charge divided by epsilon naught. The surface may be a sphere, a cube, or an irregular bubble. If it encloses the same charge, the total remains the same. Changing the shape only redistributes where the field crosses. A charge outside the surface contributes no net flux because its field enters in one region and leaves in another. This is the integral law. Locally, divergence of E equals charge density divided by epsilon naught. Electric charge is therefore the source or sink of the electric field. Now surround a bar magnet with another closed surface. Magnetic field lines leave the north end, curve through space, enter the south end, and continue inside the magnet. Every line that exits the surface must return through it. The total magnetic flux through any closed surface is therefore zero. In differential form, divergence of B equals zero. This does not mean that the magnetic field is absent. It means that the field has no isolated source or sink. Try cutting the magnet in half. Instead of separating north from south, each piece becomes a smaller magnet with its own north and south poles. As far as ordinary electromagnetism has observed, magnetic monopoles do not appear. Magnetic field lines form continuous loops. Move a magnet toward a conducting coil. The magnetic flux through the coil increases, and a voltage appears around the loop. Reverse the motion, and the voltage reverses. Faraday's law says that the induced electromotive force equals the negative rate of change of magnetic flux. The deeper statement is local. A changing magnetic field creates a circulating electric field even in empty space. What does the negative sign mean? It is Lenz's law. If the approaching north pole increases flux, the induced current creates a magnetic response that opposes that increase. Pull the magnet away, and the current reverses to oppose the decrease. With a closed conducting path, we obtain current. With an open path, the induced electric field and voltage can still exist, but sustained current cannot flow. Electric current also produces a circulating magnetic field. Ampere's original law works perfectly around a steady current carrying wire, but a charging capacitor exposes a contradiction. Take one closed loop around the wire, then imagine two different surfaces sharing that same boundary. One surface cuts through the wire and contains conduction current. The other bulges between the capacitor plates where no charge crosses the insulating gap. The magnetic circulation cannot depend on which imaginary surface we choose. Maxwell recognized the missing quantity. As charge accumulates, the electric field between the plates changes, so the electric flux changes. The term epsilon naught times the rate of change of electric flux acts as displacement current. No electron jumps across the dielectric. Instead, the changing electric field completes the law. Current density and changing electric flux can both produce circulating magnetic fields. We can now read the four equations as a single map. First, electric charge produces divergence in the electric field. Second, the magnetic field has no divergence because its lines form closed loops. Third, A changing magnetic field creates a circulating electric field. Fourth, electric current and a changing electric field create a circulating magnetic field. The first two equations describe sources. The second pair describes circulation and time. Notice the symmetry that Maxwell's correction creates. Changing B generates E and changing E generates B. In empty space where there is no charge and no current, that mutual feedback can continue by itself. This is the clue that leads directly to electromagnetic waves. In empty space, charge density and current density are zero. Faraday's law becomes curl E equals minus the time derivative of B. The Ampère-Maxwell law becomes curl B equals mu naught epsilon naught times the time derivative of E. Take the curl of Faraday's law, then substitute the curl of B from the second equation. Now use the vector identity curl of curl E equals gradient of divergence E minus the Laplacian of E. Gauss's law gives divergence E equal to 0 in empty space, so the gradient term vanishes. What remains is the wave equation. The Laplacian of E equals mu naught epsilon naught times the second time derivative of E. Repeating the argument gives the same equation for B. Comparing with the standard wave equation reveals the speed 1 divided by the square root of mu naught epsilon naught. Numerically, this is approximately 3 times 10 to the 8 meters per second. Maxwell had derived the speed of light from electrical and magnetic constants. An electromagnetic wave is transverse. Suppose it travels in the positive x direction. The electric field may oscillate along y, while the magnetic field oscillates along z. These three directions are mutually perpendicular, and there is an essential detail: E and B are in phase. Their peaks occur together, their zero crossings occur together, and their troughs occur together. They are not separated by a quarter cycle. Their magnitudes are related by E divided by B equals C. At every point, the cross product E cross B points in the direction of travel. The animation therefore shows three pieces of information at once: field orientation, phase, and propagation. The wave moves forward, but the field vectors oscillate sideways. The wave carries energy and momentum. Their local flow is described by the Poynting vector S equals 1 over mu naught times E cross B. Its direction matches the direction of propagation, while its magnitude gives power per unit area. Increase the field amplitudes, and the transported energy rises strongly. The wave speed satisfies C equals frequency times wavelength. Changing frequency does not change the basic mechanism, it changes the scale. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays are all electromagnetic waves. Their wavelengths and interactions with matter differ, but every one consists of coupled electric and magnetic fields traveling through space. Visible light occupies only a narrow strip of this enormous spectrum. These equations are not confined to a blackboard. In an antenna, accelerating charges create changing electric and magnetic fields that detach and radiate outward. In a receiving antenna, the passing wave drives charges and produces a measurable voltage. In transformers and generators, Faraday's law converts changing magnetic flux into electromotive force. Motors use the force on currents in magnetic fields. Optical fibers guide electromagnetic waves over enormous distances. Wireless communication encodes information into their amplitude, frequency, or phase. From power stations to mobile phones, radar, medical imaging, satellite links, and sunlight itself, the engineering world is built on different operating regimes of the same four laws. The complete story is now visible. Charge creates electric field divergence. Magnetic field lines remain continuous. A changing magnetic field curls the electric field, while current and a changing electric field curl the magnetic field. In empty space, those two changing fields sustain one another and travel as a wave. The constants measured in electrostatics and magnetism determine its speed, revealing that light itself is electromagnetic. Four compact equations connect circuits, magnets, antennas, energy, and the light reaching our eyes. That is the power of Maxwell's theory. Not merely four formulas to remember, but one structure that shows how electricity, magnetism, and light belong together